Welcome back to our next series on grade 10 chemistry. We're looking at redox reactions today, which is a particular type of reaction with metals, and we're going to look at how the electrons move around. A few things on the screen there. All the good jokes, argon, which is a element on the periodic table, or our Big Bang Theory down the bottom here. E full of beryllium, gold, and titanium because you're beautiful. Beryllium is Be, gold, its symbol is Au, and titanium is Ti, hence beautiful. Let's move on. Have a think about what we did last time. We were talking about the periodic table and how it's constructed and some of the groups and so on in there. You need to remember that information for today because you're going to need to draw on it. And hopefully you're not doing that sort of periodic table. So our objectives today, we're going to watch a bit of a video to recap a bit about the periodic table. We're going to look at some exercises from our textbook, which is the Jacaranda book we've been following. We'll have a look at some redox reactions, make some predictions about reactions, because that's the point of doing this, to work out how a reaction is going to occur ahead of time. Look at metals and ions. An ion is basically a charged particle, as in it's gained or lost electrons, and some applications of this. And we'll have a look at an experiment that we'll check out next lesson. So first task, have a look at this video. It's about electron configuration and the periodic table. It's only 5 minutes long, so it's not that long. Go and check that one out. It's about how the electrons are arranged in the periodic table and why it's done the way it's done. And now that you've watched that video that you should have watched on the previous slide, we're going to do some textbook work. Turn to page 158 of the book that we're using, which is the Jacaranda Science Quest edition 3, I believe we're up to. I've taken a screenshot on the bottom left of the screen there of the page that you've got to go to, and you can complete questions 1 to 9. All right, hopefully you've done that. You can check your answers in the OneDrive that I've provided for you. So now, about the periodic table. So chemists have always looked for ways to arrange elements. We noticed that elements did certain things, and we thought we need a way to put all this stuff together. And the periodic table was what we came up with. And in particular, it was a Russian scientist by the name of Mendeleev that came up with this arrangement. And it was in order of increasing atomic number. You may recall that atomic number is the number of protons in the nucleus of an atom. And in what this periodic table allowed us to do was to start to draw some inferences on how elements should react. Those in the same groups or the same columns tend to react in exactly the same way. And what it comes down to is they have the same number of valence electrons. That is, electrons in their outer shell, hence they'll react in the same way. Now, there's a little bit here about creating inferences and so on. We observe things, we collect facts, we analyze those facts and start to identify some patterns across different observations we have. From that, we will infer a reason for something occurring, and then we confirm it with a test. This is what Mendeleev did when he created his periodic table and was able to predict elements that hadn't even been discovered yet, because he looked at those groups or those columns of the periodic table and realized that they all were arranged the way he did it because they all reacted in certain ways, and hence he saw that there were some gaps that should go in there, and he was able to predict some of these elements that hadn't even been discovered yet because of that. So, making predictions about reactions. So the periodic table is not just this nice looking thing that you see on your chemistry laboratory wall. It helps us provide predictions about reactions. So we're going to look at how another way that scientists do this. We have this other little sort of table that we refer to as an activity series. It's sort of think of it as a cut down version of the periodic table, where we're specifically looking at metals and how they form ions, how they become charged particles, and how that helps them react. And so the reactivity series is about how metals react. So recall, metals have an outer electron that are held relatively loosely. Those outer electrons are their valence electrons, and they're not held very strongly in metals, and hence they can move around a fair bit within the actual substance of the metal. A redox reaction is when one metal will lose electrons and another metal will gain the electrons. all right? And we use this term redox because the loss of electrons is the oxidation part, which is the ox, and the gain of electrons is what we call reduction, which is the RED bit. So if you think of redox, that's where it comes from. We have a mnemonic that we refer to as oil rig, which is basically oxidation is loss of electrons, reduction is gain of electrons. Okay, that's a little way of remembering what's actually going on, because we're going to have two metals that react. The reaction is called a redox reaction because one metal is reduced and the other metal is oxidized, and that's why we call it a redox reaction. Let's look at this a bit more closely. So we've got a little mnemonic down the side there. Oil rig, oxidation is loss of electrons, reduction is gain of electrons. So oxidation at the top here, oxidation of a metal. So we're going to call this element M, metal M. So we have element M with a little S in brackets, means it's a solid metal, like a solid bar of metal. And it reacts and it becomes M plus an electron. What that means is we took out this negative electron out of our metal, and that meant that the metal became an ion, which is a charged particle. It's like we took out one negative charge, which is that electron, and hence the metal has a little plus sign on it now, saying it's positively charged. The AQ means it's aqueous, means it's sort of almost like it's dissolved in water. All right, an atom of that metal came off and dissolved in water. All right, that's an oxidation reaction. Oxidation is loss because he lost an electron. Probably the most common thing to think about here is iron rusting. Iron rusting is an oxidation reaction because you're losing those iron atoms off the actual bar of iron that you've got as it rusts away. Now, reduction is the opposite of this. So here's a metallic ion that we're calling X, whatever X is. It's already charged, X plus, and it's an aqueous form. That's what that tells us. That's that there. Now, the reduction is a gain of electrons because it says reduction is gain. So we're adding an electron to him. That negative charge goes with that positive charge, forming a stable atom that is not charged. And it becomes a solid atom at that point. So we have like a metal solution. It's gaining the electron and it's becoming a solid. And the thing to think about here is in these reactions, they're paired up. That electron there becomes that electron there. It gives it up to that other atom. So when the reduction reaction and the oxidation reaction are combined, we have a redox reaction. And that's what I said before. Redox is where the name comes from. Redox reactions are a good example of displacement reactions because it's like that oxidation reaction, the one we saw at the top there. We are displacing that atom. Combining the two reactions is down here, and all we've done there is just put those two reactions together. Let me just clean my slide up a little bit. So we're taking that metal atom and that charged metal atom is those two, and this guy here and this guy here are those two. Notice we don't need to put the electron into this because it's not that important in the process. It simply goes from him to that one over there. Okay, that's what this means down the bottom here. It's the net ionic equation. Okay, in other words, any substance present both as reactants and products that cancel out. It's kind of like algebra. The electron is almost cancelled out in this process because it just swaps from one atom to another, from the M to the X, and hence we don't need to show it in the equation. Notice how we did show the solids and the aqueous metals there. So to help us work out these reactions, we have this thing called an activity series that I mentioned before. So this little table that we've got here is a fairly simple version of that. Sometimes it's referred to as the reactivity series. or activity series, same really thing. What does this tell us? Least reactive metals are down the bottom here. Highly reactive metals are at the top here. Things like silver, gold, and platinum tend not to react. Silver tarnishes a bit in air. Gold tends not to react much at all, and hence you can, like a golden ring doesn't need to be polished that often because it's not reacting with the air. Silver reacts a bit more, but you've got some other metals like iron is quite reactive, reacts quite easily, as in it rusts away. Aluminium is a bit of a weird one. It's even more reactive than iron, although aluminium tends not to rust away. And that's a function of how aluminium basically, when it does rust, the rust is that sort of slightly duller aluminium that you see, which is aluminium oxide, which is basically a really, really hard layer, and it basically protects the rest of the aluminium from rusting. Think about something like iron that you can contrast it with. When iron oxide forms, when it rusts, it basically flakes off. It doesn't form that hard layer like the aluminium does, hence iron keeps rusting away. All right, and obviously right at the top there, you've got things like potassium, sodium, calcium, highly reactive metals that will really, really react very quickly and quite explosively. All right, so anyway, we've got the ones down the bottom there that tend to be found in their pure form, tend not to be too abundant, and hence tend to be quite expensive metals, things like gold, silver, and platinum. So essentially what we've written here, gold and platinum do not lose electrons easily. That's why they're not very reactive. So what does that tell you? The very reactive ones obviously lose their electrons very easily and make them reactive. So something like potassium, right up the top there, is very reactive and easily undergoes the oxidation. It doesn't hold those valence electrons very well, very closely to its atom, so it can lose them quite easily. Hence, it will undergo oxidation, because oxidation is loss. It will lose an electron very easily. So potassium is the K. It starts as solid potassium metal. It will lose an electron and become an aqueous atom, as in it's like the potassium dissolves in the solution around it, because usually these oxidation reactions happen in water. Think about iron. Where does it rust easily? In water. So if any of the metal ions of a metal below potassium are reacted with potassium, then the ions will be reduced. So what that means is we have the oxidation, the redox reaction. This is the oxidation reaction. There's usually a reduction reaction that goes hand in hand with it. Potassium's up the top there. Pick something below it, such as silver down here. Silver is below it. So what that means is the potassium is going to undergo the oxidation and give up the electron. The silver is going to undergo the reduction and accept that electron. So here's my silver, here's my potassium. The potassium becomes charged, so K plus and aqueous in the solution, and we get solid silver produced. Because it accepts that electron, it is reduced. There's another version of the reactivity series on the left there. Just to give you a little bit more detail, you can see that in the top there we have potassium becomes K plus, so that means it loses one electron. Contrast that with calcium becomes 2 plus, so it must lose 2 negative charges, hence it loses 2 electrons. And that's the extra detail that this one's shown us. Aluminium, if he's being oxidized and loses electrons, he'll lose 3. Okay, so how do we predict the production reaction when metal and metallic ions are placed together? The metal further up the series will be oxidized, i.e. it will lose electrons. The ions of the metal further down will be reduced. They will gain the electrons, and we combine the two together. So here's an example. We're adding lead and copper. All right. So what do we need to know? We need to know where they are on the table. Lead's there, copper's there. We don't need to know that it's lead metal and copper ions like it tells us here, because we can work that out. For a reaction to occur between lead and copper, lead is higher up, so it's going to start as lead, Pb, and it's going to lose 2 electrons, So we need to start with copper ions, and it will gain those 2 electrons to form copper metal. And that's what we've written here. So Pb solid becomes Pb2 plus, because it told us it becomes 2 plus there. That's why it's written there. And it's going to be aqueous. Because it's 2 plus, we are losing 2 electrons. That means there's 2 electrons for the copper to accept when it's reduced. So we must start with this form of copper, the already charged one, which is the ion, ion, ion. He will accept the 2 electrons and become solid copper metal. These two then get added together like we said before. That's the left-hand side, your reactants. That's the right-hand side, your products. Reactants, products there. And we don't bother writing in the electrons. So, can we store a solution of copper sulfate in a tin container? And this is the kind of question you tend to get in these in exams. We're putting can one particular metal substance be stored in another metal substance? And this is something chemists have to think about, because it all comes down to the reactivity of what's actually going on here. Will these two react? And obviously to do it, you need your activity series to do it. So, following on what it says, since tin is above copper in the activity series, it means tin is more reactive than copper. Hence, copper ions can displace electrons from the tin metal, causing the tin to dissolve. Note what that said just then. You look at your reactivity series, it's copper sulfate, so copper is the metal part we're interested in. It's a tin container, like a tin can or something like that. Will copper and tin react, and how will they react? Because tin is higher on the reactivity series, which means it's more reactive, it means that the copper will take electrons from the tin and dissolve the tin. And here's our 2 reactions here. So tin is Sn, will react, it'll lose 2 electrons. The copper, we start off with Cu2 plus, we'll accept those 2 electrons, and we have our overall reaction. So what is that telling you? It's telling you that if you put a copper sulfate liquid in a tin container, the copper is going to take electrons from the tin will start to dissolve, it will rust away from the inside out, and hence it will start to fall apart. So that wouldn't be a good idea. So in other words, what it's telling you is, this is the solution part, this is the solid metal part. If this one is higher on the activity series, it's going to rust away, and you cannot store those two together. You cannot put that solution in that metal container. Might be a good time to have a look at these examples here. Pause the video and head back and have a look at the activity series and tell me, is tin higher on the activity series than copper? Yes, it is. So it's still going to react with the container, but the copper container is not going to react. How do I know that? Because it's the opposite of the example we just looked at. Have a look and see where zinc and copper is, and silver and tin is on your activity series. You would expect that silver, being fairly unreactive, is going to be right down the bottom of the activity series. So this guy's going to be higher, hence they will react, as in, because these ions will accept electrons from the solid tin, the tin will dissolve, exactly like our example at the top there. Let's look at this in a little bit more detail. We have silver ions and copper metal. So silver's there, copper's right there above it. Now instantly we know that the metal is above the ion, so it's going to react, it's not going to work. How do we know that? How do we write that out as an equation? So if we have the copper part first, we start with the copper metal. That would be Cu solid, reacts to form or oxidizes, loses those electrons. Cu aqueous 2 plus, it's meant to be a plus, plus 2 electrons. And the silver ions, so we're going to start with the ion part, Ag plus, Ag plus, because it's an ion, it's going to be aqueous in a solution. Oops. Plus an electron will give us Ag plus solid. My mistake, there's no plus on that. There, that's better. Now, for this reaction to work, there are 2 electrons here, so there's going to be 2 electrons here, so we need 2 silver atoms, which gives us 2 silver atoms out the other end. And that can obviously be rewritten as a proper equation, Cu solid plus 2 Ag aqueous plus gives Cu2 plus aqueous plus 2 Ag solid, like that. Alright, they will react together like that because the copper loses the electrons, it is oxidized, the silver gains the electrons, so it is reduced. Remember, oil rig? It's going to react, so the silver is going to rust away the copper container. It won't work. Okay, let's look at another example. Zinc ions and copper. So copper was there and zinc is there. Zinc ions are higher up the activity series, so they are not going to lose their electrons to the copper because they already are ions. So they're not going to react. So that one is quite okay to store zinc ions in a copper container. And the last one, silver and tin. So silver's there, silver ions, tin's there. So the tin metal will be oxidized as it becomes charged like that. The silver will accept those electrons and be reduced. They will react, so you cannot store those two together. For all of these, writing out our equations like I did up there is always a good idea, so you get the chemical idea in your head. Alright, a few more websites for you to go and check out now. Here's a little interactive simulation to have a go at to predict the reactions of some of these oxidation reactions. There's a great little thing about the reactivity series about different metals that we have here and trying to create a surface that you can walk across that body of water. Go and check that out. Another one there about these oxidation displacement reactions. You can have a look at that one too. And next lesson we'll do a quick experiment. For those working at home, if you can find this equipment, that's great. Otherwise, we can do it when you return back to school. We're going to have 3 samples of metal, zinc, copper, and magnesium. And we're going to put all of these metals in a copper sulfate solution to predict what happens. Make sure you have those things for next time. Essentially, we're going to use a little spotting tray, a bit like this one here. And you put a little sample of copper sulfate in each of those little wells of that spotting tray. Then you put copper metal in one, magnesium in another, and zinc in another, and observe the reaction that occurs. There's a good video on Redox Reactions, these crash course ones that I suggest you go and check out, which give you round off your understanding just nicely. Another little interactive task for you to have a go at, which talks about galvanic cells. Think of kind of like battery type cells, which are basically forms of redox reactions that you can have a go at. There is where you have a go at writing half equations. That's like that bit before where I had like a metal solid reacts plus a metal charged aqueous plus an electron, and then you had the other half. They are half reactions that you put together to make the whole reaction. All right, have a think about these redox reactions and the activity series that we spoke about today. Think about what you might have learned. Next time, we're going to have a look at the practical activity. Thanks for coming.